Okay, let's get started for today. We're going to be covering inverse reinforcement learning today. And before I start with the technical content, I want to put up a few reminders. So on March 22nd, your project group and your title for your project will be due. So you make sure that you're forming groups for your project, and then we'll make a post on Piazza soon about how you specify your group and specify the title for your project. And then after that, on April 17th, your milestone report and milestone presentations will be due, and the milestone presentations will be during class. And then shortly after that, we're going to start beginning project presentations, and then the projects will be due at the end of the semester. Okay, so getting started with the technical content, today we'll be covering inverse RL. The outline is here, so first I'll talk about the motivation for using inverse RL, and the definition of inverse reinforcement learning, early approaches to inverse RL, then I'll cover maximum entropy IRL, and how we can scale IRL to neural network cost functions. Okay, so this is something that you may have seen before earlier in the course, but the motivation here is that here's a reinforcement learning agent. In this case, it's one that was trained by some folks at DeepMind to play the game Breakout in Atari. And you might wonder, so as we've learned in this course, the way that it gets its reward and the way that it gets feedback for learning is the reward. In this case, the reward is the score that's used in the game. And you've also seen this in the homework that you're doing right now. But when you get into the real world, consider this scenario where this kid wants to pour water from a pitcher into a cup. What is the reward? It's not clear. There isn't any convenient extrinsic reward that exists in the world that gives feedback for this agent until perhaps when the kid drinks the water and is satiated by the water. And so the key takeaway here is that in the real world, humans don't get a score for every action that they're taking and don't get feedback over the course of their life. There is no very clear extrinsic reward. And if you look at the scenarios where reinforcement learning has been very successful in various domains, you can see that these are domains where the reward function is very clear, such as winning or losing the game in backgammon, such as forward progress in locomotion, and such as the score or winning or losing the game in Atari and AlphaGo. But in many real-world domains, it's very challenging and very difficult to specify the cost function. For example, in the example that I talked about before with robotic, if you wanted a robot to pour water from a pitcher to a cup, you might want to actually get a cost function for that. You might need to engineer a system to detect the water in the cup and figure out how much water is in the cup, figure out if any of the water has spilled. And that the engineering effort into doing that is likely even more complicated than learning the policy itself. And this isn't just in robotic manipulation. This is also true in autonomous driving, dialogue systems, virtual assistants, and many others, where specifying the reward function is often very difficult, whereas getting demonstrations for the task and being able to learn from demonstrations is easier. And so one approach that we've seen earlier in this class to solving this problem is using behavioral cloning and using imitation learning. And the key idea behind behavioral cloning is to mimic the actions of the expert. But one challenge that arises here is that if the agent isn't the same as the agent that's actually trying to perform the task, then the goal actually isn't to mimic the actions of the expert. The goal is to achieve the outcome that the expert achieved. And so with behavioral cloning, there's no reasoning about outcomes, about what actually happens at the end of the task, and no reasoning about actually how you get there, about the dynamics. And the expert, as I mentioned before, might have different degrees of freedom of how you accomplish that task. And so it'd be nice to have a framework that can, instead of trying to mimic the actions, can mimic the outcomes, can try and reach the outcome that the expert achieved in its demonstrations. And so the question that we're going to be looking at today is, can we reason about what the expert is trying to do? And can we figure out what the expert is trying to do, and then ultimately have our agent be able to learn how to do what the expert is trying to do as well. And so formally, this is known as the problem of inverse optimal control or inverse reinforcement learning. These terms are largely equivalent, and what they mean is that we're going to, given some expert demonstrations, given rollouts from our expert policy, we're going to try and infer the cost function or the reward function for which that expert was acting. What was the cost that the expert was optimizing? And I'll also want to note that the cost or reward, so cost is just a term for the negative reward function. This is something that Sergey mentioned earlier in the course. So when I use the word cost or the word reward, they're interchangeable. And also, so a common acronym for these is IOC for inverse optimal control and IRL for inverse reinforcement learning. Okay, so formally, what does this mean? So in inverse RL, we're given the state and action space of our MDP. We're given rollouts from the expert policy in that MDP. And sometimes we know the dynamics model of that MDP as well, or the transition model. And the goal is to recover the reward function for which the expert, for which PyStar was optimizing. And then ultimately use that reward function to get a policy that can achieve the same outcome and optimize the reward function that the expert was optimizing. And another approach to imitation learning that we saw early in this class was Dagger. And one comparison to Dagger here is we're not going to assume direct access to PyStar. So we're not going to assume that we can collect additional demonstrations from our expert or be able to query what the optimal action is for a certain state. We're just going to assume that we have demonstrations, we have rollouts from our expert, and that's all we can use from our expert. Okay, so why is this a challenging problem? What makes this hard? So first, it's an underdefined problem. So there's many possible reward functions, many possible cost functions that that are possible given the rollouts. So for example, you can scale the reward function, and that will result in the same optimal policy. There are other transformations as well. Like for example, the reward function might be 1 if you achieve the goal and 0 otherwise, or it might be more shaped than that. And because it's an underdefined problem, because there is this ambiguity, it makes it a challenging optimization problem. The second challenge is that once you have a cost function or a reward function, it's difficult to evaluate it. So say you have a reward function. I don't know, does anyone have ideas? How would you actually evaluate that reward function? How would you determine whether or not that reward function is good with respect to PyStar? Okay, so yeah, it's clearly a challenging problem. How do you actually evaluate this? Typically, one of the ways that people evaluate it is solve for the optimal policy with respect to that reward function, and then compare the optimal policy, compare the policy that with respect to that learn cost to the expert policy. As you might imagine, that's a bit efficient, and we'll talk about ways to deal with that later in this lecture. And then the last challenge is that the demonstrations might not be perfect. So if your demonstrations are coming from a human, if they're coming from some expert, they might not be precisely optimal with respect to some reward function. And if your algorithm is assuming that they're exactly optimal, then you're going to run into issues, and you're not going to recover the reward function that the optimizer was actually optimizing. Okay, so I guess, does anyone have any questions on the formulation before I move on to approaches for solving this? Okay, so some early approaches. So I guess actually one thing that I wanted to mention, I guess, is so inverse optimal control was originally proposed by Kalman in '64, and inverse RL was formally introduced by Andrew Ng and Stuart Russell in 2000. And all of the early approaches to inverse reinforcement learning, like I talked about before, alternate between solving the MDP with respect to your current cost function and updating your current cost function using that policy. The initial approach in 2000, when the term was introduced, was proposed to find a cost for which the expert actions have higher value than all the other actions. And generally, a larger gap is better. So generally, the larger action, the expert actions should have high value, and all the other actions should have lower value. And then in 2004, Peter Abeel and Andrew Ng built upon this framework and built upon this formalism by saying that the expert policy with respect to the cost should match the feature counts of the expert trajectories. And what I mean by feature counts is the expected features. So they're using a feature-based representation, where you have features of your trajectory. And they're saying that the expert policy with respect to your cost function that you're learning should exactly match the expected features under the trajectory distribution of your policy, should match the feature counts of the expert trajectories. And then another formalism was introduced in 2006 by Nathan Ratliff, and this was more similar to the original formulation, and it used a max margin formulation between the value of the expert and the value of the expert actions and all the other actions that you might take. And so one of the issues with all of these formulations is that they acknowledge the fact that there's ambiguity in what cost function is in how the expert takes actions and what cost function is the true cost function, but they don't handle that ambiguity. And for example, if you have this margin approach where you're trying to have the expert actions have high value and all the other actions have low value, there's no reason why that gap should be large. So making the gap larger between those actions isn't necessarily what the expert intended. And so what we really need is we need a principled approach to model how the expert is acting and kind of where the noise is coming from and how the expert is acting with respect to a cost function. And the other thing that these approaches don't handle is what if the expert isn't perfect. Okay, and then, so now what I'll be talking about is maximum entropy IRL. So this was proposed by Brian Ziebart in 2008, and this proposes a solution to both of the questions that I talked about before with ambiguity and with the demonstrations not being perfect. And the reason why I'm going to focus on it today is because it's a widely used framework in inverse reinforcement learning, especially when combining it with deep neural networks for the cost function. And it offers a principled solution to these problems and through a probabilistic framework. Okay, so first I want to go through some notation when I introduce this. So I'm going to denote a trajectory with tau, which is your sequence of states and actions. I'm going to use cost instead of negative reward. The cost is going to be denoted with C, and it's going to have parameters theta, and we're going to be trying to learn the parameters theta. And on the board, I might drop the subscript on C, but generally it's going to be parameterized by theta. And in the linear case, so this is in the original maximum entropy IRL paper, they used a linear cost function. So C theta was equal to theta transpose F, where F is the features of your trajectory. And that was defined to be a sum over the states in that trajectory of theta transpose times the features of the state. So it was decomposed over time. And then I'm going to use D, capital D to denote the data set of demonstrations, and I'll use M to denote the number of demonstrations that we have. And lastly, I'm going to use T to denote the transition dynamics. And now I'll go to the whiteboard and I'll leave this up for reference when going through this. And this is mostly so tau and T are things that you've seen before. The main new things with this notation is that we're going to use C theta to denote the cost, and we're going to have this data set of demonstrations that we're learning from. Okay, so in Maxent IRL, the way that we model demonstrations and model the expert is we're going to say that the probability of a trajectory of appearing in our set of demonstrations is going to be proportional to e to the negative cost of that trajectory. And so what this says is that trajectories with equal cost are all going to be equally likely to be executed by the expert, and trajectories with higher cost are going to be exponentially less likely. And so the expert is going to have some noise. It's not going to be always outputting perfect trajectories, and sometimes it's going to be outputting trajectories with lower cost, but the probability of those trajectories is going to be exponentially less likely. And one thing that you can show is this is saying that the objective of the expert, instead of being to minimize cost, is going to be to minimize, so where pi is the policy, we're going to be minimizing the expectation of that policy of the cost of the trajectory minus the entropy of that policy. And so this is where the randomness comes in. Okay. And so now using this model, how do we determine the cost function? How do we learn the cost function? So the objective that we're going to be using is we're going to say that theta, the parameters of our cost function, are going to be the result of maximizing the log likelihood of our demonstrations. So we're going to take the log and then take a product over the demonstrations in our data set of the probability of that demonstration trajectory.
Should there be a max?
Oh, yes, sorry. So we're going to have this optimization problem that's taking the argmax over theta, and this is the log likelihood of our demonstration trajectories. And so one thing we can do is we can transform this into it. We can take the product outside of the log, make this a sum over our demonstration trajectories in our data set of the log, and then I'll substitute e to the negative cost in here. And note that this is proportional to, so p of tau is actually equal to 1 over z, 1 over our normalization term of e to the negative cost. So this will be 1 over z, e to the negative cost of tau d. And I'm also going to, so because we often do minimization problems in optimization instead of maximization problems, I'm also going to make this a negative, and then we're going to be actually minimizing, with respect to theta, the negative log likelihood of our data. And then one more thing before I move on to solving this, I'm also going to put a 1 over m here, which will be convenient later. But that 1 over m term doesn't affect the optimization problem, and doesn't affect the solution to the optimization problem. Okay, and note here that z is equal to the sum over all possible trajectories of e to the negative c of tau. And in the case where your state and action space are continuous, this will be an integral. And in the case where you have discrete states and actions, it's a sum, because you'll have a finite number of trajectories. So I'm going to start with the case where we have discrete states and actions. Later we'll talk a little bit about continuous states and actions, but in this paper, as well as in the next paper that I'll talk about, we're only considering finite and discrete states and action spaces, and that will make this problem a lot easier. Okay, so let's expand this objective function out a little bit more. So if we can actually separate this objective out into two parts because we have a log and a product, so it can become 1 over m sum over tau d. I'm going to drop the d here for convenience. And then the log of e to the negative cos. This becomes c of tau d. We can also remove the negative signs now since there's 2 of them. And then the second term with z is going to look like, you can take the negative into here, and because this is an z inverse, we can make it z. And so this will be plus log of z, which I'll substitute here, t e to the negative c of tau. And where the 1 over m went, so this is a sum over tau d, and we have a 1 over m, but there's m demonstrations, and so that will cancel out because this doesn't depend on tau d. Okay, so this is our objective, and for a linear cost function, it turns out that this is actually a convex function, which means that there's a single solution, so there's no ambiguity in the solution for theta. Oh, and this is for a linear cost function and for a deterministic MDP. This is convex. And so we can solve the optimization with gradient descent, and assuming that we can evaluate this. So what the gradient looks like, let's denote this by L. This is our objective, and the gradient of L with respect to theta, what this is going to look like is 1 over m sum over tau d dc tau d d theta plus, and then the gradient of this term is going to look like 1 over the sum over all possible trajectories of e to the negative c of tau times the sum over all possible trajectories of e to the negative c tau, and there is also a negative term in here, which I'll put in here because of the negative cost, times dc of tau d theta. And this is all in parentheses. Okay, so this is the gradient. One thing that's still a bit challenging to compute here is the sum over all possible trajectories. We don't want to have to enumerate all possible trajectories because this can be very inefficient. And so we want a more efficient way to compute that. And so let's go through that. So let's focus on this term right here. This term is fairly easy to differentiate to compute the gradient of. We just need to differentiate through our parameterized cost function. But for this term, one thing that you might notice is you have there's this e to the negative c of tau here, and then there's this term right here, which is essentially the normalization factor for this. And so note that the probability of a trajectory is equal to e to the negative c of tau divided by the sum over all possible trajectories of e to the negative c of tau. So this, if we bring this normalization term inside, we actually get the probability of a trajectory. So this is equal to the sum over all possible trajectories of the probability of this trajectory given your current cost function parameters theta and your transition dynamics times dc of tau d theta. Does that make sense? And so first off, why does this depend on theta and our transition dynamics? So this is the probability of a trajectory. The probability of a trajectory is going to be a function of theta because that's what determines our policy that we're acting under. And then the transition dynamics is because that affects our distribution of the next state given our current state in action. So note that, I guess I can't really write here for visibility reasons. I'll write in a different color up here. So note that the probability of a trajectory is going to equal to the probability of your initial state times the product over the probability of AT given ST times the probability of ST plus 1 given ST and AT. And so this right here is our policy under our cost function. We can denote that as pi, and then this right here is just our transition dynamics. Okay. So how are we going to compute this probability value? I guess the next thing to note, and the last part of this math here is that we can actually take the sum over all possible trajectories and turn it into a sum over all possible states. So because our cost is a sum over the states of the features times the parameters, this is equal to a sum over states of the probability of hitting that state given theta and our transition dynamics, times dc of s d theta. And this term right here is called our state visitation frequencies. So this is the probability of being in state S, generally. And what this looks like in the linear case is, note that d theta is going to be equal to our features. So if in the linear case, if our cost function is theta transpose times our features, then d theta is just equal to f of s. So this would be f of our trajectory, and this is f of our states. Okay. So now how do we compute our state visitation frequencies? So I guess, yeah, next I'll talk about that. Up until this point, are there any questions on the math here? Okay, so there's a way to compute the state visitation frequencies using a dynamic programming algorithm. And let's see. I need some more whiteboard space, so I will erase this. I'm going to keep up the objective for now. So our goal is to compute this P of S given theta and T. And so step one for computing, so our goal is P of S given theta and T. And so step one is going to be to compute pi of A given S with respect to a cost, with respect to C theta. And this is our optimal policy given with respect to our current value of our cost function. And the way that you can do this is just using value iteration for if you have discrete, if you're in the tabular setting where you have discrete actions and discrete states. So I'm not going to cover how we've done this how you do this since we've covered value iteration in this course. And then, so this is step one. Step two, so we now have pi of A given S, and we know our transition dynamics P of S T plus 1 given S and ST and AT. Now we need to compute our state visitation frequencies. And the way that we do that is we can first actually compute the state visitation frequency at time step t, and I'm going to denote this as mu t of s, and this is the probability of visiting s at time t. And then once we compute all of these, then we can actually just sum over all t to get the visitation frequencies here. So the way that this dynamic programming algorithm looks like is we start at our first state, mu1 of s, and this is going to be equal to the probability that s1, our initial state, is equal to s. And then we're going to iterate, we're going to take a forward pass, we're going to iterate for t equals 1 to our horizon, and then we're going to set mu of t plus 1 of s is going to be a sum over all possible actions and all possible previous states. I'm going to use s prime to denote previous states. Note that you normally use s prime to denote the next state. In this case, it's the previous state. So the probability of hitting state s at t plus 1 is the probability of being at the previous state at time t times the probability of hitting state times the probability of taking an action A from the previous state times the probability of landing in state S given the previous state S prime and action A. And then to get the probability of a state given theta and t is just going to be equal to a sum over all t of mu t of s. Any questions on this? So this is much more efficient because we don't have to actually enumerate all of the possible trajectories to get these state visitation frequencies. We can actually pre-compute and take a forward pass, pre-compute mu t of s, and then we're going to use that at the next time step iteratively with dynamic programming. Yeah?
Just simply propagation on the chain, right?
Yes. And so that's how we get our state visitation frequencies. Okay, so what does this look like as a general algorithm? So in taking a step back from the math, so what this looks like as an algorithm is first we're going to initialize the parameters of our cost and gather our demonstrations. Then we need to compute this state visitation frequency, so we're going to solve for the optimal policy with respect to c theta using value iteration. Then solve for the state visitation frequencies using the dynamic programming algorithm that I just talked about. Compute the gradient of our objective with respect to our parameters using this formula right here, where I replace dc d theta with the features. So this is in the linear case. And then update our parameters with one gradient step using the gradient that we just computed. And then repeat. So we iteratively solve for the state visitation frequencies by solving for the policy, compute the gradient, and then take a gradient step on our cost function. Okay, so after this, we'll take a short break before talking about scaling to nonlinear and to deep neural network functions. After the break, I'll see if there are any questions. I'll let you digest this a little bit and see if there are any questions. But we'll take a 2-minute break now.
So like basically the main one is that like the data is you actually generate rather than like a box. So if you look at and then I say I get a box and I get like
Okay, let's get started again. Are there any questions with the math here or anything that wasn't clear? Yeah.
what is the F here?
F is the features. So I'll go back one slide. So in the linear case, the cost function is equal to theta transpose times the features. So this is a feature vector that is encapsulating the trajectory or the states. And you could see F being the state of your system, or features that are incorporating the state. Any other questions? Okay. So next we're going to talk about how we can scale this to the nonlinear case, where our cost function isn't a linear function, but it's a neural network function. And generally the main difference, so steps 0 through 2 are going to be the same. In step 3, what's going to be different is that instead of having those features here, we're going to have dc d theta here. And so just to compute the gradients with respect to our parameters, we're just going to use backpropagation to compute dc d theta instead of having just the linear terms there. And so a paper that did this, the paper that did this was, I guess there's two papers. The first paper that proposed the initial algorithm appeared in the DeepRL workshop in 2015. This is work that was done at Oxford. And then they actually applied this to some path planning that I'll talk about in a little bit in urban environments using this algorithm. And so this setting is we still have the setting of known dynamics with discrete states and actions, the tabular setting, and we're going to use a neural network to represent the cost function. And so the way that they're doing this is they're largely considering these cases where you have this tabular state space where it's this kind of 2D grid, and often what this represents is they're considering navigation problems, but this is representing the top-down view of the world, so a 2D map of the world from the top down, and they have some feature representation of this 2D map, which I'll discuss what that could be in a minute. And what the algorithm looks like is first you initialize your weights. This is basically the algorithm that we just talked about. We initialize our weights, then run our neural network forward to get the reward function. Then they run approximate value iteration to get the policy with respect to that cost function or with respect to that reward function. Then propagate the policy to get the expected feature count, to get the expected state visitation frequencies. Determine the gradient using maximum entropy IRL with respect to the neural network parameters. And then update the weights using your gradient, and then repeat. And so note that you need to, as before, you need to iteratively solve the MDP, iteratively solve for the optimal policy, as well as the state visitation frequencies for every weight update that you do for your neural network policy. And so nonetheless, they were able to apply this to a fairly real-world problem. So they had this golf cart that had Velodyne LiDAR sensors and a stereo camera. And the way that they were representing their features, the input to the neural network, is they computed for every kind of voxel, or every 2D grid cell, they computed the mean height of that cell, the height variance, and the visibility of that from the sensors. And the red lines here are showing the demonstration, or one of the demonstrations for this kind of navigation problem and this obstacle avoidance problem. And they collected 120 kilometers of demonstration data and then segmented this into, I think, around 25,000 demonstration trajectories, where each demonstration trajectory was around 15 kilometers. They compared, so in this kind of map that was showed above, they also designed a cost manually. So this is an example of the cost for the settings that are shown above, where higher is better, so or higher, darker costs on this map correspond to higher costs. And so what this is kind of showing is that the open space is going to be low cost, that's yellow. The grass, which is shown in this turquoise color, is going to be medium cost, and then the obstacles, which are, in this case, dark blue, are going to have the highest cost. And then they compared MaxNet IRL with 3 different neural network architectures, standard, pooling, and multiscale. For the details, you can see the paper, to this manually designed cost function. And they evaluated the method on a test set of demonstration trajectories and evaluated the negative log likelihood of those held out trajectories, as well as this distance function between trajectories, and found that using the learned cost, using a neural network cost, is able to significantly improve the negative log likelihood of the test trajectories, as well as decrease the distance between the trajectories using the learned cost versus the manually designed cost. Okay, so kind of the strengths and weaknesses of this method. So first is it's able to scale to neural network cost functions, and it's efficient enough to work with a real robotic system. Some of the limitations is that you still need to repeatedly solve the MDP within the loop of this inverse RL algorithm, and you assume known dynamics. So assuming known dynamics actually isn't very limiting of an assumption for these navigation tasks, where you're just saying that, I mean, I know if I'm going to command my robot to move to a different position in the world, then you kind of know what's going to happen. You know that it's probably going to get to that position. In navigation settings and settings where you're using position control, known dynamics is a fairly reasonable assumption. But if you're in the setting like robotic manipulation, or other settings where you have contacts and it's harder to have this dynamics model, then that's going to be a severe limitation. Okay, so what about unknown dynamics and continuous states and actions? And for this, I'll go back to the whiteboard. And let's see. I'll erase. So in this setting, we computed our partition function exactly by computing the optimal policy and then computing the state action visitation frequencies. And when we have continuous states and actions and when we have unknown dynamics, we can't do that because we don't know P of S given S prime A. And so we're not going to try to compute it exactly, and instead we're going to try to approximately estimate our partition function using samples. So this is still our objective, and this is still our gradient. And I'll also erase this. And this. Okay. So our goal is to estimate this value. And actually in the continuous case, this would be an integral over all possible trajectories of e to the negative c of tau d tau. So you essentially just replace the sum with an integral. And the way that we're going to estimate this, and really one of the only ways we can estimate this if we don't know the dynamics, is we're going to estimate it using samples. And in particular, we're going to use importance sampling. So in importance sampling, you sample from some distribution and use that to estimate your value. So our goal is to estimate this value right here, and to estimate this value, what we're going to do is we are going to draw samples, which I'm going to denote with tau s, from some distribution q, and then approximate this as e to the negative tau s divided by the probability q of tau s. And this is an unbiased estimate of this because of the normalization factor. And one of the key questions here is, what distribution do we sample from? Where do we get q? How are we going to get a distribution to sample from? And so if you think about it, the distribution that q should be is it should be, so for minimum variance of this estimator, we want our distribution q of tau to be proportional to the magnitude of e to the negative c of tau. And this is just saying that where we have higher values, we want the probability to be higher. And also note that this is e to the negative cos is always going to be positive, so this is just e to the negative tau. Or it's always going to be non-negative. Now note that this is the optimal distribution to sample from for minimum variance of this estimator. And note that this distribution is the same exact distribution as the one that we're trying to get in the first place. So it's clear that this distribution is going to be hard to, we don't know this distribution. It's going to be hard to figure out. Just if we had one try, we're not going to be able to guess it very accurately. And so what we're going to do is, what we can do instead of just trying to guess a single q, we can adaptively construct a q using our current estimate of c. And try and get closer and closer to the distribution q that has minimum variance for this estimator. And so kind of the key idea here is to adaptively construct q. And note that q is a distribution over trajectories, and so a way to construct q is just to optimize a policy, to construct a policy that approaches this distribution. And so to get q, we're going to, at each step of the algorithm, we're going to try to get a q that approaches this. So we're going to try and essentially just use this objective, which is, I guess this will be an argmin with respect to q of e to the negative, the expectation under q of c of tau minus h of q. So this will be the way that we update q, the way that we adaptively update q to get a better estimate of the partition function. And then the last thing that I'll write on the board is that if we're going to be adaptively updating q, we don't want to throw away all of our old samples from all of the old q's when we're computing this objective. Because for example, if we're in a robotic manipulation scenario, taking samples is expensive, so we're going to have multiple q's. We're going to have multiple samples. We're going to have samples from different q's that we want to keep around and use to estimate our objective function. And so when you have samples from multiple q distributions, the right thing to do is to construct a mixture distribution over your distributions. And so say you have capital K different distributions, then this mixture distribution is going to look like essentially the average qk of tau, the average over all of your q's. And then what this objective function is going to look like here is this is going to be, or approximately, be 1 over m sum over your demonstrations, c of tau d, plus log sum over your samples, e to the negative c of tau s divided by v of tau s. Okay. So that's the math. What does this look like as an algorithm? So this is a paper that appeared in ICML last year. And kind of the goals were to remove the need to solve the MDP in the inner loop. I haven't talked about how we're doing that yet, but I'll talk about that next. Be able to handle unknown dynamics and to be able to handle continuous state and action spaces. And so what the algorithm looks like is we start with an initial policy pi 0 and human demonstrations. And pi 0, you can also, in this case, you can replace that with q0. So this is an initial distribution over our trajectories that we're going to be sampling from to estimate our partition function. Then we're going to generate samples from pi. So these are going to be our tau s that we're going to be using to compute the partition function. Then update our cost using the samples and the demonstrations. So we're going to take our samples and run gradient descent with our gradient. And we don't have to take a single gradient step. We can actually take multiple gradient steps because this is an estimate over our gradient. And then we're going to update our q, on the slide, update our pi with respect to the cost. We'll update our distribution q using this objective here to make it closer to the distribution that, closer to the minimum variance distribution for importance sampling. And so the result of this, so you iterate that, and eventually at the end of the algorithm, your q of tau should be e to the negative cost, e to the negative c theta, and the cost should be will be iteratively approaching the true cost function using this importance sampling estimator. And so at the end, you have both your cost, which is being optimized, as well as a policy. So your Q is optimizing this cost. It's using this objective to optimize the cost, and that's actually your demonstration distribution. So you actually end up both with a cost and with a policy. And the key thing in this algorithm is that instead of actually fully optimizing for the Q with respect to this distribution, we're only going to partially optimize Q. And so this is how we can avoid solving the MDP. Is we're just going to take actually a single step on Q at each step of this iteration, rather than fully optimizing your distribution. So kind of the key insight here is that we're going to update our cost in the inner loop of this policy optimization algorithm. Okay, and then for those of you that are familiar with generative adversarial networks, if you're not, that's fine. If you are, this will actually look a lot like a generative adversarial network, where this cost optimization is actually discriminating between the demonstrations and your samples. So if you look at this, this gradient right here, or the objective right here, it's trying to make the cost of the demonstrations low and the cost of the samples high. So it's essentially trying to discriminate between the samples of your policy and the demonstrations. And your Q is actually is trying to optimize, is trying to make the samples look most like the demonstrations, and trying to kind of trick the discriminator into thinking that the samples actually came from the distribution of the demonstrations. And you can actually show mathematically that for a certain form of discriminator, this is actually exactly equivalent to generative adversarial networks. Then another thing that I'll expand on next is that also at the same time, Jonathan Ho, who was a PhD student at Stanford, also developed a very similar algorithm that at a high level looks very similar. At a low level was actually derived very differently. But it has this, it also has the structure of iterating between optimizing for your policy and optimizing for your cost. Okay, so kind of going back to the math, what this looks like is we're going to be initializing our queue and then iteratively generating samples from queue in step 3, appending those samples to our existing set of samples, using our set of samples and the demonstrations to update our cost using gradient descent, using this gradient, the gradient of this objective right here, then updating our trajectory distribution using this objective with respect to our current estimate of the cost function. In this case, you can use really any trajectory optimization method or any policy optimization method. In this case, we were using ILQG, which we covered earlier in this lecture, and then iterate once you have your new queue. And at the end, you return your optimized cost parameters and your trajectory distribution queue. Okay, so far it's been all math and algorithmic. What does this actually look like if you run this on a real robot, on a real system? We also ran this on simulated domains, but the real world domains are more exciting to watch. The first task we did was to place a dish into a dish rack. And in this case, the state included the goal pose of the plate. And the second task was to try and pour almonds from one cup to another. And the reason why we didn't do water is because this is not a waterproof robot, and so if you put water near the robot, then bad things will happen. And in this case, the state X, the input to the cost function included unsupervised visual features that were learned with an autoencoder. Actually, the spatial autoencoder that you heard about a couple lectures ago. And then the action in this case was joint torques. So with joint torques and with these sorts of things, we really don't know the dynamics, and so this sort of method is needed. And then we compared our method to 2 other IRL methods. One is called path integral IRL. The other is relative entropy IRL. And what these methods did is they had some initial distribution Q, generated samples from that Q, and used those samples to estimate the partition function, and that was it. They didn't adaptively construct Q. They just picked an initial distribution, which in relative entropy IRL was a uniform distribution, and in path integral IRL was a distribution that was roughly tracking the demonstrations. And so, as you might imagine, when you're just picking that distribution, it's going to be very biased. It's not going to be it's going to have a lot of, your estimate of your partition function is going to have high variance, and so you're not going to be able to get a good cost function as a result. Okay, so here's me collecting demonstrations for the dish placement tasks. So we collected 20 demonstrations. We held out one of the positions of the dish because we care about generalization to new settings. And then one other baseline that we included was we just used the standard cost function that we use for a lot of our manipulation tasks, which is something along the lines of minimizing the distance between the current plate position and the goal plate position. And so here's the result. And as you might notice, it's fairly aggressive. We actually broke a plate during training. And you can also see that it actually, because the plate bends a little bit, it actually doesn't reach the goal. And this isn't to say that we probably could hand engineer a cost to do pretty well at this task. So this isn't to say that you couldn't do that. But in general, it's easier to provide demonstrations than to try and engineer a cost and use trial and error to try and figure out a cost function that's good for this task. Here's the baseline method. So here's relative entropy IRL on the task, and you note because because it can't get a good estimate of the partition function, it's unable to complete the task. And then here's using the algorithm that we discussed before, using guided cost learning, and you can see that it's able to gently place the plate into the rack, like the demonstrations, qualitatively similar to how the demonstrations were placing the plate, and also get it into the correct position. Okay, and so the second task was to pour almonds from one cup to another. So Here are 3 of the 20 demonstrations. The first 2 were fairly close positions of the cup. Here's a further position of the cup. And here's the baseline method. And as you can see, the robot isn't able to figure out the cost because of the inaccurate partition function estimate. And then here's the policy learned with guided cost learning. And so it's able to accurately move the cup to the goal and get the almonds into the goal cup. Yeah.
So why did for training or for collecting data? Why didn't you put almonds in there?
I didn't put almonds in the cup during training and during the demonstrations because I didn't want the almonds to go everywhere and have to manually clean up all the almonds during training. And in practice, they didn't weigh a lot, so it was okay to do that. Yeah. Okay, and so in both of these settings, in the settings, well, in the results that I was showing for guided cost learning, I was showing the policy. I was actually showing Q, the final trajectory distribution that was learned using guided cost learning. But one of the things that I know before is that you actually get both a policy and a cost function. So the conclusion from here is we can recover successful policies. One question that you might have is the cost function also useful for new scenarios? So if we take the cost function and then re-optimize it for a different position, here's the result for the plate task. And you can see that it's able to successfully place the plate and gently place the plate into the rack. With the cup task, we actually found that in some settings it was able to successfully perform the task by re-optimizing the cost. And in other settings, it seemed that it was overfitting a bit and wasn't able to successfully complete the task. So generally, kind of a conclusion from here is that the policy tends to overfit less and it is more successful than the cost function. And again, kind of drawing the analogy to GANs, for those of you who are familiar with it, note that normally the GAN discriminator is discarded, and in this case, the cost is representing the discriminator. And so in this case, the generator is the thing that's more useful than the discriminator in practice. Okay. And then the last thing that I'd like to cover is the paper that I mentioned before by Jonathan Ho at Stanford. And the method was basically the same as guided cost learning that I talked about, that I just covered. And the main difference is that the demonstrations came from a TRPO optimized policy. So TRPO is trust region policy optimization. It's actually a policy optimization method that you'll hear about next lecture on Wednesday from John. It's based off of policy gradients, very similar to policy gradient methods. So instead of coming from a human, they came from an optimized policy because all of the tasks were in simulation. And in simulation, it's hard to gather human demonstrations. And then instead of using ILQG as a policy optimizer, they used TRPO as a policy optimizer during training to get the samples to optimize for Q. And then they performed the method on tasks in the OpenAI gym, which you saw in the first homework on imitation learning. So here are the results of their methods. So you can, they normalize the performance. So the dotted blue line shows the reward of the performance of the expert. The dotted green line shows the performance of random. And then the light blue line for each of these tasks shows their method, the generative adversarial imitation learning. And you can see in all of the cases, it's able, and I guess the other thing is the x-axis. So the y-axis shows the normalized performance. The x-axis shows the number of demonstrations. So in this case, they actually didn't show the number of samples. They only were comparing against the number of demonstrations. The number of samples is actually something that's pretty important to consider, especially if you want to run this on a real robot. Because they were using TRPO, it inherited the same sample complexity as TRPO, which generally requires many, many samples on the order of tens of thousands or millions of time steps. And Whereas if you use a more efficient trajectory optimizer, like the method that we showed before, that's able to work much more efficiently because we're using a more efficient policy optimization method. So back to these plots, the blue line is showing TRPO, which is able to match the performance of the expert in almost all of the settings, and also using a fairly small number of demonstrations. The orange line is showing behavioral cloning, which we talked about before. So it's able to reach higher performance using fewer demonstrations than behavioral cloning. Probably with many more demonstrations, behavioral cloning would do better. But you can see here that inverse reinforcement learning is more efficient than behavioral cloning. And then the pink and the yellow lines are showing baseline inverse RL inverse RL methods that I won't cover here. Okay. So to conclude, I'd like to conclude with some kind of pros and cons with these methods, and also open limitations for inverse reinforcement learning methods in general. Since these methods are really, right now, the current state-of-the-art methods, and for your project, you might be interested in extending on them and building upon them and making them better. So the strengths are, first, that we can handle unknown dynamics by sampling. So instead of assuming that we have our transition dynamics and assuming that we can compute our partition function exactly, we're going to sample from the environment to be able to estimate our partition function. We can scale to neural network cost functions, which is important, and is also, if you use an efficient policy optimization method, you can also run this on a real robot and be efficient with that policy optimization method. The limitations are that the adversarial optimization is hard. So because you have these two, you kind of have this two-player adversarial game between the policy that you're optimizing and the cost that you're optimizing, this optimization can actually be quite hard to get working well. And for those of you that are at all familiar with working with generative adversarial networks, you're probably familiar with that challenge as well. The second is that you can't, we haven't seen yet the ability to scale to raw pixel observations. So in this case, we were using kind of the raw state of the system, which included either like visual features or the joint angles of the robot and such, but we're not able to yet scale to just seeing a video of a human perform the task. And lastly, the demonstrations typically are collected with kinesthetic teaching or teleoperation. They're collected using the system, and there isn't a domain shift problem like we talked a lot about last lecture. Okay, since I have a little bit of time, I actually want to cover an additional thing, which is that I talked earlier about this ambiguity between about what cost function is correct. And in the linear case with maxent IRL, we can actually get rid of that ambiguity and get a single cost function. But when you move to neural network cost functions, that ambiguity comes back because we have many more parameters. And that ambiguity becomes more of a problem. And so one of the things that we found that was necessary in guided cost learning is we actually needed to regularize our cost function such that ambiguity was mitigated to some extent. And so we used two different regularizers. There's this ambiguity, IOC is underdefined, and we use two different regularizers. And so these regularizers, the first one I think is very broadly applicable to inverse RL, which is that we can encourage the cost to be slowly changing. And what this means is that generally you shouldn't have a cost that is over a trajectory, isn't rapidly changing between different values and isn't spiking with different values. And so the way that we encourage it to be slowly changing and to be fairly smooth is we penalize approximation of the second derivative of the cost. So this first term is the slope of the cost between t and t plus 1. The second term is the slope between t minus 1 and t, and we're going to penalize the difference between those slopes. You could potentially do something more sophisticated if you can measure the curvature of your function, but in this case, we're just using a local approximation to encourage it to be slowly changing. And generally, your cost should exhibit this principle. And the reason why we did slowly changing rather than just having it be slow, rather than just like penalizing the difference between c at xt and c at xt minus 1 is that if you penalize the second derivative, this is going to encourage your cost functions to look like fairly straight lines, whereas if you penalize just the difference between your cost at a certain time step and the next time step, you're going to encourage it to have zero slope. And we don't want it to have zero slope in general. And this is, of course, local. So yeah, it's done at a local level. The second regularization term that we use that is perhaps a bit more specific to robotic manipulation tasks is we encouraged the demonstrations, on the demonstration trajectories, we encourage the cost of those demonstrations to decrease monotonically in time. So generally at the end of a manipulation task, you're going to assume it's natural that the cost of that demonstration will be lowest at the end and highest at the beginning because it's trying to reach some goal. And so we can encourage this monotonicity by using a form of a hinge loss between neighboring time steps of the cost, as shown in this equation. And then we also ran an ablation on 2 of the simulated tasks that we compared. And so here, the x-axis is showing the number of samples taken, and the y-axis is showing the distance to the goal. So this is a learning curve where lower is better. The dark red color is showing using both of the regularizers that I discussed. The blue is showing without the monotonic regularization, so we see some benefit from the monotonic regularization. And then the green is showing without that smoothness regularization, without the first regularization, which we see a dramatic improvement with that regularization. So these are 2 possible regularizers that you can use to deal with that ambiguity problem when you're scaling to neural network cost functions. And there are definitely other possible regularizations that you can use or come up with, but these are a couple. Okay, with that, I'd like to conclude. And so next time on Wednesday, John we'll be going back to forward reinforcement learning rather than inverse reinforcement learning, and John will be covering advanced policy gradients, including trust region policy optimization, or TRPO. See you on Wednesday.